Hey y'all, welcome back to Alakazam Math Made Easy. In this video, we're going to go over what's called Lhopitals Rule. And it kind of connects to a topic that we brought up at the beginning of this lecture series, but haven't really talked about much since then, right? So we know that derivatives and limits are connected, right? By the formal definition of a limit, that's the limit as x approaches h of f of x plus h minus f of x all over h. And remember, that's the one where we expand out the x plus h part and then cancel all of the terms that they have in common with f of x. And then we factor out an h out of the numerator, cancel it with the h in the denominator, and then take the limit as x approaches, or sorry, as h approaches 0 of all of the remaining terms, right? And that should cancel to get us to what we actually can calculate using the derivative rules, which are much easier, but that's still a valid option. But because limits and derivatives are so interconnected like that, it's important to also know that you can use derivatives. So we can use limits to help find derivatives, but we can also use derivatives to help find limits, right? And there was an issue that we brought up earlier on where we needed to evaluate a limit and we got it to equal 0 over 0, but we couldn't figure out exactly how to interpret that result because it doesn't really mean much mathematically. That's what's called an indeterminate form, where the final form of your answer is not helpful in terms of a conclusion you can provide. So 0 over 0 is one of them. But infinity over infinity is one of them, 0 times infinity or 0 times negative infinity, 1 to the infinity, 0 to the 0, infinity to the 0, and infinity minus infinity. So there's a couple things to notice in these cases, right? So if you can remember far enough back from when we initially started doing the solutions for 0 over 0, we were able to factor something out of the numerator and the denominator. Usually it was some x minus a term out of both the numerator and denominator, and that allowed us to cancel the terms that were making it 0 over 0. But if you think about it, there's no way to really cancel out the term that's making it infinity over infinity, right? Because it's not as easy. We were able to take advantage of the fact that if one of the factored pieces equaled 0, that would cause the whole side of the function to equal 0. Whereas that's not necessarily the case with infinity or 1, right? So what we'll do from here is we'll we will jump into what's called Lhopitals Rule. And again, this is the way that we can use the derivative to help us find a solution to that issue we had before, the indeterminate forms. So this is the formal way of writing it here, where if we were originally taking the limit as x approaches a of some function f of x divided by some function g of x, we can apply Lhopitals rule and turn that into the limit as x approaches a of the derivative of f of x over the derivative of g of x, right? So that's a huge benefit for us because a lot of times it'll be easier to take the derivative of those functions separately as opposed to factoring stuff out in the first place. So an important thing to notice here is we're not taking like quotient rule. This is not going to be a quotient rule thing because we're not taking a derivative of this whole chunk, right? What we're doing instead is we're saying, all right, I'm going to first take the derivative of this and put it over here. And then I'm going to take the derivative of this and put it over here. So we're not taking the derivative of the relationship of functions. We're taking the derivative of the two functions that are being related. So that's a little bit different. And it's a little bit tricky for a lot of people to remember that. So a note on format that a lot of professors are kind of stickler about, like they're kind of picky about making sure you write it this way. If you'll notice here, I wrote this little arrow with an LH on top of it, right? So some professors do not like when you write it like this with just a normal equal sign, because technically those two things, I mean, they do mean the same thing, but they are not saying the same thing, right? They ultimately will get you to the same thing, but they don't equate, if that makes sense. I don't really know how to describe it in terms of why that's not right. But the general rule of thumb is because you're using, you couldn't look at this function itself here and get from one step to the other if you didn't tell the reader that you're using L'Hopitals rule. And that's why they use this format here, is because that's the way of saying, hello, reader, I got from here to here using L'Hopitals rule. And that's helpful for people to follow along with your work, which is hugely important in an academic standpoint because your professor is grading your work, right? So here are the general steps. So you first of all always test the value, right? Because if I can, for example, plug in 1 right here and it doesn't work out to 0 over 0 or whatever, then it doesn't matter. I don't even have to use L'Hopitals rule. I can just plug it in and go. If you do get an indeterminate form, that's when you use L'Hopitals rule. So apply it, right? Take the derivative of the numerator, take the derivative of the denominator, reevaluate the limit, and if you still get an indeterminate form, do it again. Just keep doing it until you don't get an indeterminate form anymore. So what we're going to do here is evaluate a function where it only takes one go to get from an indeterminate form to an answer, right? Sometimes it only takes once. So as you'll see, I plugged in 1 here and got 0 over 0. As a reminder, I very easily could just factor this and cancel the term that's making it 0, but there's no necessary guarantee that that'll be easy to do, right? So that's generally why, even if the function does look like a polynomial, by this point, you shouldn't be factoring. You should just be using L'Hopitals rule unless they ask you to factor. So from here, we know that it's 0 over 0, and we know that we need to use L'Hopitals rule. So what we're going to do is we're going to take the derivative of this top one, which becomes 20x cubed minus 8x, and that's what we got here. And then we're going to take the derivative of the bottom part, and that's going to be -1 minus 27x squared, and that's what we got here. Again, notice we did not use quotient rule. We did not do low d high minus high d low over low low. We did not do that. We took the derivative of the numerator, put it back in the numerator. We took the derivative of the denominator and put it back in the denominator. So that's a hugely important step, an important thing to remember, because you won't get the right answer if you do quotient rule. And then another thing to just point out, I did use that formatting here with the arrow and the LH. And then what I did is I just evaluated the limit, right? I plugged this 1 back into all of the x's that I had and simplified again, and that got me to an answer that wasn't indeterminate, right? I could evaluate what this actually means. That gives me an actual number that I can look to. So that's an example of where it's pretty simple in terms of you only need to do it one time. This is going to be an example of what we need to, or what happens if we need multiple steps to get out of this indeterminate form, right? So again, the first step, we're going to plug in infinity. So that becomes x approaches infinity, becomes e to the infinity over infinity squared, which is essentially infinity over infinity, right? If I raise e to a massively high number, it'll become a massively high number. If I square a massively high number, it'll become a massively high number. So here we have an indeterminate form. And again, you can kind of walk yourself through the logic about why this is not a helpful answer, right? Because technically, one rule tells us that a number over itself should equal 1. One rule tells us that if we have a number over infinity, that it should equal 0, right? Because the denominator is massive. And another rule tells us that if we have infinity over some number, it should be infinity. So this kind of points us towards 3 different evaluations that really don't help us because it doesn't point us to 1. So we know it's an indeterminate form. So what I'm going to do is I'm going to do by L'Hopitals rule, the limit as x approaches infinity. That doesn't change. And I'm going to take the derivative of it, right? E of x stays e to the x, right? Because that's the rule for that. And then 2x or x squared becomes 2x. And then I'm going to reevaluate it again. That becomes e to the infinity over 2 times infinity, which still works out to infinity over infinity. So I still need to do it again. So again, by L'Hopitals rule, the limit as x approaches infinity. That becomes, again, e to the x over now 2, which gives me e to the infinity over 2, which is just infinity over 2, which is infinity. And even though that's not like an actual number you could plot, that's not indeterminate. I can conclude that the graph goes to infinity. I can draw something from that. So that is an application of derivatives that really helps simplify one of the things that we brought up at the beginning of this lecture series, right? Indeterminate forms are something that we started the class with a little bit. And derivatives made that process much easier. So as always, if you learned something from this video, please like it. To stay up to date on the content that I post, subscribe to my channel and turn your notifications on. If you still have questions after watching this video, please drop them in the chat. I'd be happy to answer them. Or not in the chat, I'm sorry, in the comments. So I'll answer those there. And then beyond that, as always, best of luck.